Hi everyone, thank you for clicking this video and thank you for your interest to our projects. Today, I'm going to present our new paper. The title is Strategic Pricing and Routing to Maximize Profit in Congested Roads Considering Interaction with Travelers. This paper has been accepted in Transaction on Control of Network System. My name is Young-Suk Kim. I'm a PhD candidate at Cornell University. This is the joint work with Ning Duan at Cornell University, Joella Giardini at MIT, Samita Samarnayak at Cornell University, and Damon Wisgate in Cambridge University. In high level, we want to model the equilibrium of strategic behavior of stakeholders. In mobility system, we have multiple stakeholders, including governments, travelers, and mobility service provider. What we try to do is to model the strategic interaction between travelers and mobility service provider so that we can evaluate the government's intervention. However, modeling this in complicated transportation network is extremely challenging. To be more specific, here is the application that we try to model. We are considering multiple transportation network company, say Lyft and Uber. And each company operate their own service. And one company can operate multiple service. For example, Uber operate UberX, UberXL, and Uber Premium. There are also multiple travelers, so this is the multi-agent game with conflicting goal. Companies tries to maximize their profit by optimizing their pricing and routing strategy. Their routing decision affect their travel time in congested roads. When the services are provided, travelers choose one of their best options to maximize their utility. And they consider travel time in congested roads and the price that company set. The traveler's decision may influence the market share, which is related to company's profit. So company need to revisit their decision. So they will adjust their pricing and routing strategy until it reached to a point where further changes wouldn't increase profit. So we define these states as company travelers equilibrium. And given the complexity of the problem, we are focusing on a special case, assuming a single company. And after successfully formulating the problem for a single company, we are thinking of solving the same optimization problem multiple times to get some empirical evidence of equilibrium in competition situation. This is the problem that we want to solve. The decision variable, pi, is price. We have objective function, which is maximizing profit. And profit is calculated by revenue minus operation cost. And revenue can be calculated by multiplying demand by choice probability by price. We have constraint for vehicle and passenger flow in network, and we also have another decision variable related to routing decision. But today I'm going to focus on pricing piece of this formulation. We have constraint expressing the choice probability as a function of price. And F, you can think this as a multinomial logic model. And this nonlinear constraint makes this entire problem intractable. The solution idea is really simple. We are expressing price as a function of choice probability by taking an inverse function, and we plug it into the optimization problem, objective function. Then we can write the equivalent Q problem, and luckily, the objective function turns out to be convex in terms of choice probability theta. And we successfully convert the domain from price to choice probability. Since Q problem is convex programming, it is tractable. So after obtaining the optimal value for choice probability, we can plug it into the inverse function to calculate the optimal price. So using this trick, we were successfully modeled the interaction between travelers and mobility service provider through a convex model to characterize the equilibrium. The input of our model is city-related characteristics, including network, fuel cost, tolling, travel demand, and value of time. And as an output, we can obtain all the socially important metrics. Then we can evaluate the government's intervention, including investment, incentivize, and taxation. And our network analysis with dynamic effects can complement the conventional microeconomics policy assessments.